Ji, Assalamu alaikum students. I hope you can hear me loud and clear. Just let me open the book for you. Today we are going to complete the topic of DC motors. The last type of DC motors is DC series motors. We have already done the shunt motor and the separately excited motor. Today we are going to do the last topic, which is DC series motor. After that, only the last section of DC generator would be remaining, and inshallah we will be completing the course. And your assessments from CLO4 I'm going to schedule in the next week, and I'm going to tell you how I will schedule them. Okay, so just let me open the book. Six. Four. Series motor. Okay, here it is. Let me share the screen with you. Okay, now I hope you can see this screen. So this is the last of the motors that we are going to discuss. We have already done the DC shunt motor and the DC uh, separately excited motor. So this is a type of a motor in which the field windings and the armature windings are connected in series, which has some interesting effects for this motor. Remember, in the separately excited motor, the field winding was in a different circuit and the armature winding was in a different circuit, and both were excited by DC sources. And in the shunt motor, the field windings and the armature windings were connected in parallel, and in both of these motors the field, keeping the field constant, was not an issue. Okay, in the separately excited motor, we had a completely different circuit for the field, so the armature current was not affecting the field, and the armature current can also be thought of as the current which is drawn by the motor to drive the mechanical load. Okay, so in the shunt motor also the field winding was connected in parallel to the armature, and since the field winding was getting a constant voltage Vt, so we were assuming that the field was constant, and it had nothing to do with the load current or the armature current, just like in the separately excited DC motor. But in the shunt DC motor, as the field and the armature windings are connected in series, so the field has a direct relationship with the load on the motor, because if the armature is drawing more current, if the motor is driving a heavy mechanical load, then the
देखा
field,
भी
current would also increase.
बट
And
मुझे वापस ज्वाइन करो तो ज्वाइन करनी पड़ेगी
please turn off your mics. Okay, please turn off your mics. You may use chat to communicate with each other. If you want to talk to me, only then unmute the mic. And similarly, if the mechanical load on the motor is decreased, and the armature current would also be decreased because it will require lower torque, so the field would also go down. So the field has a direct relationship with the uh, load on the motor, because the armature current is directly proportional to the load on the motor. As the load is increased, there's a requirement on the increase in the torque. So we remember these two equations, they are also valid here. So the two equations that we are constantly dealing with is armature induced EMF is equal to K phi omega m, and torque is equal to, induced torque is equal to K phi Ia. Okay, so whenever the load on the motor is increased, you need a higher torque, and that means the Ia must increase. Okay, and when the motor is driving a lower mechanical load, then the torque induced must decrease. So the motor would require a lower value of armature current. And the armature induced EMF EA has a direct bearing on the field and omega m. But in the previous two types of motors, this field was almost constant, or it was relatively easy to keep it constant because the field had no relationship to the armature current. But over here we see that the field will have a relationship with the armature current because the field and the armature coils are connected in series. Okay, so the circuit is shown over here. Next page probably. This is a circuit for a series motor. So this part you can see is the field. The field resistance is shown as RS and the field inductance is shown as LS. So this is the field part and this part is the armature part. So the field over here is it is very difficult to keep it constant because it has a direct bearing on the armature current. It has a direct bearing on the mechanical load. As the mechanical load is increased, IA would increase, so the field would have to increase. The mechanical load is decreased, IA would be decreased and the field would be lowered. Okay, so we have to consider this equation when we are doing the analysis. This is the equation. Okay, so the field coil is connected in series in the circuit, so the supplied voltage is equal to the sum of the back EMF or the armature induced EMF plus IA times RA plus RS, where RA is the resistance of the armature and RS is the resistance of the field. Okay, so the very important digression in this type of a motor is this relationship. Okay, so this is a generic relationship that the induced torque in any motor, AC machine or a DC machine, it has a direct bearing on the flux. It is directly proportional to the flux times the armature current. This is true for even the AC machines, synchronous machines, as well as the DC machines, as we have done before. So as we move forward, uh, this relationship we have already done now, and the armature current is same as the series current is the same as the load current. Okay, because the load current is also the current which is drawn from the supply by the motor, and you can see it is similar to the IS and it is similar to the IA because all of these things are connected in series, and we know in series the current is the same. Now this is a relationship which is new for you, and this relationship only applies to the series machine. Okay, it doesn't apply to the shunt motor or the separately excited DC motor. It only applies to this series DC motor. And what does the relationship say? That flux is not independent in this machine, as was the case with the separately excited motor, as was the case with the shunt motor. But here the flux is a function of the this armature current, because you can see that the two field and the armature coils are in series, so it has a direct bearing on the armature current. Armature current has a direct bearing on the load driven by the motor, because that would determine the value of EA, that would determine how much torque is required. So the flux is not independent or constant in this machine. We always have to consider that flux is a function of the load current of the machine or the armature current of the machine. And we know this relationship. This is a generic relationship for all DC and AC machines. The torque induced is a proportional to the flux times the IA. And since the flux is itself a function of IA, so the net relationship is that flux, when you replace flux in terms of the IA, then the torque relationship goes as the square of the armature current. Instead of just the linear relationship, it goes into a squared relationship with the armature current. Okay, so how does this uh, uh, change the further analysis of the machine? So we have already been doing this terminal characteristic of the DC motor, in which we want to see the torque speed characteristics of the DC machine, where we plot the speed on the y-axis, and we plot the torque of the machine on the x-axis, and we see that how the RPM of the machine changes with the increase in the mechanical load. Okay, torque has a bearing with the mechanical load, because as the mechanical load is increased, the machine requires more induced torque to drive the load, and vice versa. So in the previous relationship of the uh, shunt motor and the DC separately excited motor, we saw some sort of a relationship like this, that with increasing torque, the RPM would slightly decrease, which is an expected relationship, but it was decreasing very, very gradually, not very sharply, as the gradient of this line was not uh, uh, very much high in magnitude. It was showing a decreasing trend, but a little bit decreasing trend. So now we want to do the same thing for the series motor. So for the same analysis, we again start with this Kirchhoff's voltage law equation, and this new relationship that we have seen, that the flux in this machine is a function of the, it's not constant, it is constantly changing, it is a function of the armature current or the load current. So uh, from the relationship, that torque is equal to, which we have already driven over here, torque is equal to KCIA square. It's not a linear function of the armature current, but a squared function of the armature current. And we make IA as the subject of this equation. So it will become torque divided by Kc, torque induced divided by Kc, whole under root. Okay, so this thing comes from this expression. And now we substitute values in the expression for the KVL, Kirchhoff voltage law. So Vt remains as it is, and I know Ea is a function of the flux and the K, phi, and omega m. So I'm going to replace Ea with this relationship. This is a generic relationship for all DC AC machines. We have already been doing this for the synchronous machines. And over here, we can substitute IA with this new found expression over here. So IA is substituted by this RA plus RS. Okay, so this again looks like a relationship between omega m and torque, but the only problem is I want to isolate my omega m on the left hand side, and I want my torque variable on the right hand side. So now the problem is both the this omega and the torque variables are featuring on the right hand side of the equation, and the other problems are that we want to get rid of phi, because I want a graph of omega m versus torque. So this variable should be a function of the torque, and other variables such as flux and these things should be eliminated. These things are constant. Okay, so I am not very worried about this. This K is a constant, C is a constant. I'm not very worried about this. So up right now, and this is also constant. I'm not worried about this. So the only thing which is bugging me now is that I should get rid of this flux, which is not a constant, which is not a function of the architecture of the machine. It's a variable. But I know that I can express this variable in terms of other variables. Like in this particular series machine, I know this relationship. Flux is a function of Ia. So what I can do is uh, I can try to get rid of this flux by using this relationship, that torque induced is equal to this expression. And how I got this expression is because I know torque induced is equal to uh, KCIA square. Okay, KCIA square, I know this. And I also know that Ia is equal to phi over C. Okay, so I basically replace this phi over C square over here. So it becomes KC and phi square over C square coming from here. And this one of the C gets cancelled with this. So I get this expression, that I can get a relationship between torque induced and phi. So what I'm going to do is I'm also going to replace this phi in terms of torque induced. So if I may phi the subject in this equation, I get this, and I'm going to replace this phi over here. Okay, so that I'm only getting torque induced or omega m, but not phi, which is again a variable, and I want to get rid of this. So I make the required substitutions. Vt is equal to, and I replace this phi with this gadget here. So it is k times this gadget times uh, omega m, and this expression I was already happy with because I have torque induced in this, and all the other remaining things are either constants or they are architectural components of the machine which we are not changing while a machine is in operation. Okay, so we make omega m the subject of this machine by shifting this term over here and shifting this term over here. And in terms of the omega m, the relationship goes like this. So now we can see that this is not a linear relationship, it is a non-linear relationship, because this is not obeying the y is equal to mx plus c like before. So this is a non-linear relationship because the y variable is omega m and the x variable is 1 over under root torque induced. Okay, so this is not a linear relationship, it is a non-linear relationship. And when we try to plot this on the curve looks like this. Okay, so the torque speed characteristics for a, you can call it the torque speed characteristics for a series motor, series DC motor looks like this. And now you can see it is unlike the shunt and the separately excited, which were slightly drooping characteristics. This is a curve in which the RPM decreases very, very sharply as the torque is increased or as the mechanical load is increased, because torque is directly proportional to the mechanical load. Higher the mechanical load driven by the machine, the more torque it will require. Okay. So another important thing to note is if there is no load, mechanical load on the machine, that means that the torque goes to zero on this side. And look what happens to the RPM. The RPM starts to go to infinity. So as torque goes to zero, the RPM of this machine starts to go to infinity. And that is why it is always said that you must never operate a series motor without a load. Okay, so always remember this. This is a question you may be asked in an interview, job interview. So we must never operate a series motor without a load. If someone says this, and why is this so? So you can always quote this curve that as we see the torque speed characteristics over here. In the previous analysis of the shunt and the separately excited motor, this line had a clear y-intercept. That means at no load, the machine would run at some constant finite RPM. Okay, so if this type of a uh, if this type of a motor, which is DC shunt motor or series motor, separately excited motor is used, you could operate it without a no load, because when the torque in that case went to zero, the RPM had some finite value. But in the case of the series motor, as the torque is going to zero, you can see the RPM is tending towards the infinity. So you can never operate this machine on no load. If you do, then the machine will develop a very high RPM, and it can damage the mechanical construction of the machine. So that is why you must never operate a series motor without a load. The series motor has always to be used with a load. Okay. And another thing to note is that this machine has a high starting torque. Okay, so these are the two defining features. has a very high starting torque, because as you see, when the motor is connected to a load and when it is just started, when the RPM is at 0, then you can see that the torque is way ahead in the line. It is having a very high value, and as the motor speeds up, the torque starts to decrease. So we are just considering the starting torque here when the motor has just begun working and its RPM is just close to 0 and it is just starting from a rest. So the two defining features of the DC series motor are that it has a high starting torque, and number two is you must never operate a DC series motor without a load, otherwise its RPM will jump to infinity. Is let's do this very simple problem, then we are going to do some more end of chapter problems. Okay, so this is again a series motor. This is the terminal voltage VT, and the sum of the armature resistance and the field resistance is given as 0.08 ohms. Okay, and now it says there is some magnetization curve shown in this figure 822, which is the next figure after this. We look it in a while. Find the speed and the induced torque of this motor when the armature current is 50 amperes. Okay, so this is what we have to do. We want to find the speed and the induced torque of this motor when the armature current is 50 ampere. So now loaded with these equations and these relationships, can we do this? Okay, we have got this data, and the series field consists of 25 turns per pole. So in this type of DC machines, you especially in the series, okay, the third defining point is, I can write over here, high starting torque. You must never operate a series motor without a load. Third point is field coil has only a few turns. Its field coil has only a few turns. It doesn't have got many turns. This is another defining characteristic. And in this case, the series field consists of 25 turns per pole. Okay, so the series field has 25 turns per pole, and you will normally be getting data like this for series motors or maybe other motors also, that in the magnetization curve, when we were doing synchronous machines, you were getting the graph of field. IF was the field current that you were giving to the rotor, and on the y-axis you had armature induced EMF. So you will have a similar curve in the DC machines, but the difference will be that EA will be given on the y-axis, but on the x-axis the field may be given to you in terms of MMF, which is the product of the number of turns, and the uh, MMF was equal to NI, right? So number of turns multiplied by the current. So instead of just the current, you may be given the field in the form of MMF, and this is the same as here. Okay, IF was also a indication of the field, of the primary field of the machine, and MMF is also an indication of the primary field of the machine. But instead of giving it in the form of IF, you are giving it as a product of I and the number of turns per pole. So, but still this is an indication of the field of the machine. So this is one difference that you will get in the topic of DC machines and in the topic of synchronous machines. So always remember this. So it says that a curve is given and we want to find the speed and the induced torque of this machine when the armature current is 50 amperes. Okay, so now you have been given this curve, and again, as I told you, that the field is not given in terms of IF, but it is given in the form of the product of NI, which is MMF, which is also a indication of the field. And on the y-axis, you again have the EA just as before. And this curve is for a particular RPM of 1200 and you can read off from this curve any values for EA versus the field at this particular RPM. So now what we have and what we haven't got is, let's check. Okay, so in this relationship, let's see how we can find the speed and the induced torque of this machine when the armature current is 50 amperes. Okay, so for 50 amperes, we use our KVL relationship. VT is equal to EA plus this gadget. So if we make EA the subject, it is VT minus this gadget. Let's plug in the things. So we know EA is equal to VT. It's given to us 250 volts. The RA plus RS combination is 0.8 volts ohms, and IA is 50 amperes. So this is the operating point of the machine at which we have to investigate the machine. So at our operating point, EA is equal to 246 volts, and we want to find the omega at 246 volts EA. Okay, so we want to find omega at this operating point. Okay, so this is the operating point of the machine at which we want to find the omega. But we also know that if this IA is given, then we can also investigate the field of this machine, because IA and IF are same. The field coil and the armature coil are in series. So if IA is known, then IF is also known. It is same as 50 amperes. And the magnetomotive force will be equal to the product of Ni, and N is already given to us as 25 turns per pole. So we multiply by the 2 and we get an operating point which is 1250 ampere turns. So now what we can do is, we want to find the RPM at this point, and we have a graph which is for a specific RPM of 1200. So what we can do is, we know this relationship. This is a very popular relationship, K phi omega m. Okay, so if I know one operating point in which I know EA and phi and omega m, then I can find another operating point in which the EA and phi and omega m will be proportional. Okay, so but now in this one, we assume that phi is constant. We are not touching the phi. We keep the phi as constant. That means EA is proportional to omega m. So EA1 is equal to omega 1 divided by EA2 is equal to omega 2. Okay, so now if we assume phi to be constant, so what is the value of EA at 1200 RPM? I can read it off. So at 1200 RPM, if the field is 1250, we are not changing the field. If the field is 1250 RPM, 1250 ampere turns. So let's read it off from here. 1250 is coming somewhere here. At 1250, the field is somewhere like 70, 50, this should be 75. Okay, and at 1250 it is something like 70. Let's assume it is 70. EA is 70 at 1200 RPM. Okay, let's assume this is 70. So at 1200 RPM, EA1 is 70. This is our first operating point. And our second operating point is, we want to find the omega 2, and I already know the value of EA. It is equal to 246. So we calculate the new value of omega 2. Please quickly calculate this and tell me. So if you calculate this, you will get some value close to this. Okay, please note that we had read off this value as 70, but if you read it carefully, I think this value comes out to be 80 instead of 70. But we are just reading it off, so there can be some minute differences. But please note this change. This is a typo in the book. Over here, it should be 1200. Okay, so when you calculate this, omega 2 comes out to be something close to this value 3690. Okay, and the second part is, we also want to find the torque. So for always in all the DC machines, remember this formula, that P converted for the motors is equal to the electrical energy finally reaching the armature. Okay, because this energy will now be converted to mechanical energy. Okay, so when you supply it with the electrical energy, there will be some electrical losses and core losses, and after that the energy in the armature will be equal to the product of EA and IA. That is always termed as P converted in the DC motors, and it is also equal to its mechanical counterpart, which is tau induced times omega m. So this is the part where mechanical losses haven't been considered yet, and after you consider all the mechanical losses from this, then the real mechanical output power P out becomes equal to torque load multiplied by omega m. So torque induced omega m is the initial mechanical power developed, which is equal to the electrical power final remaining in the armature, which is EA and IA. And if someone says what is the P out of this machine, then you always remember, okay? So from here, how you can find the P out? P out will be equal to P converted minus the P friction and other losses, okay? Friction and the P stray losses. So this will be equal to the P out of this machine. And P converted is the developed mechanical power, and the developed mechanical power is equal to the input electrical energy minus the mechanical losses. So always remember this, that P converted is equal to the input energy minus the electrical and the core losses. So always remember this when you are solving and doing the power analysis. So over here, P converted is equal to the initial electrical energy, final electrical energy reaching the armature equal to this mechanical power developed. So now you can use this relationship and you can find torque induced. Torque induced is equal to EA IA over omega m. But you will use the data of your operating point, not 1200 RPM operating point. So your operating point is when EA is 246, IA is 50, and you develop your relationship for your own RPM, and in this equation RPM must be converted into radians per seconds, because you have to do this in all the SI units, and this will be the torque. So is everyone clear about this? Are there any questions? So I've also discussed the power analysis of this DC motor, and the power analysis is very similar to the synchronous machines. But in this machine, the converted power in a DC motor is equal to the final electrical energy reaching the armature. So P converted is equal to EA times IA. This formula is valid for all the three types of the DC motors. And this is also equal to the developed mechanical power, which is torque induced times omega m. So P converted will always be obtained from this relationship. It is equal to Pn minus the electrical loss minus the core loss. And from P converted, P out relationship is that P out is equal to P converted minus all the friction and stray losses. So always remember these two relationships. They will help you to do the analysis of all the DC motors. And the same equations will be reversed when we are doing the DC generators. Everyone okay with this? Okay, so we are now going to try to do some end of chapter problem. We have finished the topic of DC motors. Inshallah, next time we will do the DC generators, and I will hopefully try to, again, this non-linear analysis is not part of our course. We are going to consider only the motors which will have the compensating windings. Okay, we will never do the machines in which uh, there are no compensating windings. We are going to do only the questions which have no armature reaction. Okay, so let's go to the end of chapter problems. Try to do one or two problems. Okay, here are the end of chapter problems. And you will see these problems are much simpler than the synchronous machines. but you again have to refer to these graphs and find your own operating point. Okay, so the first 12 problems are related to the following DC motors data, and in the problem 8.1 to 8.7 you are assumed that the motor is connected in shunt. Okay, so you assume that this data is for the motors which is connected in shunt, and let's see. Okay, so you have a magnetization curve shown in figure 8.1. So where is this figure 8.1? P 8.1. Okay, it's over here. So this is for the RPM of 1800 RPM. Okay, and on the x-axis you have the shunt field current IA. So as I told you that on the x-axis you will always have something to depict the field of the machine. So sometimes the field of the machine is given in the form of the current, uh, field current. Sometimes it is given in the form of MMF, which is ampere turns. Okay, but still it is a depiction of the field, so you should never worry. Okay, so if this R, let's first draw this figure. So it is a shunt motor. In a shunt motor, you have VT and you have something going in the field. Okay, so this is LF, this is RF, and you have something R adjustable. Then you have this armature and armature resistance. This is RA, this is EA. So this is your field. R adjustable is used to control the field, so it is on the field circuit. So now you have some data. VT is 240 volts, okay, and RA is 0.19 ohms, and you have equivalent circuit of this motor shown in P8.2, figure P8.2. Okay, so this is the circuit. Okay, this is 240 and RF and R adjustable and RA. So we have drawn the circuit correctly. Okay. If the resistor R adjusted is adjusted to 175 ohms, what is the rotational speed of the motor at no load condition? So this is not a series motor, so you can drive this motor in the unloaded conditions. Try to figure out how you are going to do it, then I'm going to give you a hint. Okay, so first of all, what you can find from this data, you can find from this data that R adjustable is 175 and RF is 75. So you can find IF. Okay, so IF is equal to 240 divided by R adjustable is 175 plus RF is 75. So 175 plus 75. So how much would be the value of IF? How much would be the value of IF? IF will be equal to, quickly tell me on the chat window. Okay, so I'm just plugging in this data in this equation, and IF is the current which is going in the field branch. So I can calculate IF by dividing 240 by R adjustable plus RA. Okay, so the answer comes 0.96. Thank you, Anam. So IF is 0.96 amperes. Okay, so I can read off some values for this IF, and the curve is for uh, 12, how much RPM? It's for 1800 RPM. So at 1800 RPM, if the shunt field current is 0.96, so we are reading something here. 0.96 is something here. At 0.96, EA is 240 volts. Okay, so EA is equal to 240 volts. At IF is equal to 0.96 amperes, and omega at that point is 1800 RPM. Okay, so we have found one operating point. And now what does this guy say? What is the rotational speed of the motor at the no load conditions? Okay, so that means there is this new thing which is called no load conditions, and at the no load condition, I've already told you that at no load condition, IA will go to 0 because the motor is taking only minimal energy, and the minimal energy is only to maintain the field of the machine. And IA is 0 because when the motor is unloaded, I do not need to develop any torque. Okay, and I know that torque relationship is equal to K times phi times IA. So if IA goes to 0, then the uh, torque induced also goes to 0. Okay, let's call this torque induced. Okay, so uh, so now my operating point will be that IA goes to 0, and when IA goes to 0, if IA goes to 0, what happens to EA? EA will go to 240 volts. EA will go to VT. Because of the relationship, the relationship is VT. If the outer loop is considered, VT is equal to EA plus IA RA. And we already said that IA goes to 0 at no load. So at no load, VT is equal to EA. So at no load, EA will become 240. At no load, EA become 240. And at the loaded condition, EA was equal to, I just find out. What did I find out? EA okay. Maybe I need to look at it carefully. We were reading it off at 4.96, okay? So at 0.96, the value is slightly more than 240. Maybe it is equal to 242. Okay, so let's make this change over here. It's not 240, it is 242. 1800 RPM, the EA is at 242. And at our value of 240, what will be the new RPM? You can find it, it will be something very close to 1800 only. Okay, so at our new RPM, new value of EA of 240 at the no load conditions, okay, we can find it, and this value will come out to be something close to 1800, and I have with me 1790 RPM. Okay, so this value is very close to 1800, but you have to carefully read this curve for 0.96. So it will not be exactly be equal to 240, something deflected from 240. And the answer is this. Has everyone understood this? Okay, if you had just read off the value of 240, then the answer would be same. So at even the no load speed, it would be 1800. But if you read the curve carefully, then you are going to see that for 0.96 amperes field current, the value is slightly deflected from 240. Maybe it is 241 or 242. Okay, so it is just a matter of how you read the curve. Is everyone okay? Okay, so let's do the next part. Next part, assuming no armature reaction. So we do the questions without any armature reaction. What is the speed of the motor at full load? What is the speed regulation of this motor? So how we can find the speed of the motor at the full load? At full load, it means that the motor is doing 30 horsepower of mechanical work. And if it is doing 30 horsepower of mechanical work, then its speed should slightly decrease over the no load speed. So we want to do this for uh, the full load. Okay, at full load, they have given us that the IL is 110 amperes. What I can find from this IL is that the full load current drawn by the machine is 110 amperes. And of that part, let me open the whiteboard, or let's look over here. That that at full load, the machine is drawing. How much did it say? 110 ampere at full load. But does that make any change to the field? If I'm not I adjusted my field, so the field current will continue to be 0.96 amperes. And that means my new full load IA value would be equal to 110 75. Okay, have I changed the R adjustable or the field? Part B. Assuming no armature reaction, what is the speed? Okay, so we haven't changed that. The R adjustable is still at 175 and the field resistance is still at 75. Okay, so my new value of IA will be equal to 0.96. Okay, so this is 0.96 and this will be equal to 110 minus 0.96. So the new value will be equal to how much is this? My IA full load value 110 minus 0.96. This is equal to 109.04. Okay. So my new value of armature current is 109.04 amperes. This is for the full load operating point. Okay. So how I can find the EA at full load? So EA at full load will be equal to VT minus IA full load, which is 109 times 0.19. So how much is my new value of EA full load? EA full load new value will be equal to about 219 volts. Okay, please verify this answer. So now in the proportionality equation, I have EA1 is proportional to N1 and EA2 is proportional to N2. So now I need two operating points. I know the second operating point. At full load, my EA is 219. I want to find the RPM. The other operating point is the no load RPM, no load point, or my previous operating point, which was no load point only. Okay, so my no load point was that my EA was 240 and my RPM was 1790. Okay, so quickly give me the value of the new full load speed. New full load speed will be equal to how much? New full load speed would be something equal to how much? Quickly give me the answer. Has anyone found it? What is the new full load speed? Anam, have you calculated it? 1628. Okay, so now this also makes sense. Whenever you are doing the question, you should also do the reality checks. And the reality check is as you load the machine, the RPM should decrease. So initially, the RPM was 790 RPM at no load for these particular conditions, and the RPM has indeed reduced when the motor was operated at the full load, but little bit. We know that the shunt motor and the separately excited DC motor have very good speed regulation. So the speed regulation is uh, no load speed minus full load speed over the full load speed. So the full load speed is 1628 and no load speed was 1790. No load minus full load over full load. So how much this speed regulation is coming? Quickly tell me. No load minus full load over full load, I think. It is full load or no load? Just let me check. Speed regulation is no load minus full load over full load, I think. Okay, what was the formula for voltage regulation? I think it was V no load minus full load over full load. Okay, just please verify this formula. Anam, am I right? I just I'm feeling confused. It is no load minus full load over full load. Is this formula right? Okay, no load minus full load over full load. Okay, I'm right. So how much is this speed regulation? Has anyone calculated this? Okay, so whatever answer, that will be your speed regulation. The speed regulation is calculated for motors. Voltage regulation is for the generators. So we have already done the first part and the second part. And now we are going to do the third part. If the motor is operating, okay, I think the time is up. It's 10:30. You must be have to go for the other class. Class leader, just send me the attendance, and I expect you to do all the remaining parts. And the only catch in the DC machines is you just have to map one operating point to the other using the proportionality equations. The algebra is very simple. It's just a LCA level algebra. There are no phasors involved and anything. You just have to map one operating point to the other by knowing which variables are constant and which variables will be changed. So you can easily solve the other ones. And inshallah, next week we will do the DC generators. Okay, just send me the attendance, class leader, and hopefully you have submitted the CEPs. I will also check your CEPs, and I've also graded all of your previous quizzes and all the assignments. And next week there will be last quiz on CLO4. I will not give any assignment from CLO4. There will just be a quiz from CLO4, and it will be just based on the class practice and stuff what we have done in the CLO4. And after that, I will just take one CLO improvement quiz also. All that will be in next week. By Monday, I think I will be completing your syllabus by completing the last topic of DC generators. Okay, Allah Hafiz, and class leader, just send me the attendance quickly.